Hello. In this video, we are going to show how to display the quantum harmonic oscillator eigenfunctions in the program Microsoft Excel. The eigenfunctions have the general form of the psi sub n. The capital N is the normalization constant. These h sub n's of y are the Hermite polynomials, and then these are all multiplied by a Gaussian function, e to the minus y squared over 2. The allowed values of n start at 0 and then work their way up through the integers. The particular combination of symbols that we're using for the variables, which vary in different sites, are going to be those that are used on the site Hyperphysics, which is an excellent site that I've used many, many times before. And that's one of many widely used schemes for how to represent these eigenfunctions. In this scheme, the variable y is equal to the square root of alpha times x. Alpha itself is equal to m times omega divided by h, where that's Planck's constant. Omega is the angular frequency, so that's equal to 2 pi times the linear frequency, nu. Physicists often write this as 2 pi f. And then we have the reduced Planck's constant h bar, which is h, the Planck's constant, divided by 2 pi. We begin with a new worksheet. In cell B3, we put the label mass 1. And then in cell C2, we put that mass in terms of atomic mass units. For the second atom, basically going for a diatomic molecule here. In cell B4, we have the label mass 2. And then in cell C4, we have the mass of the second atom in atomic mass units. In cell B5, we have the label mu for the reduced mass. And then in cell C5, we have a formula to calculate the reduced mass based upon the mass of the two atoms involved. And then in cell D5, we show that the label, the units for this quantity mu, are going to be kilograms. In cell B6, we have the label H for the Planck's constant. In cell C6, we write the value of that constant in scientific engineering notation. And in cell D6, we note that the units are joule seconds. In cell B7, now we have H bar. We calculate the value of that in cell C7, and then again, the units for this quantity in cell D7 are going to be joule seconds. In cell B8, we have the label speed of light. Cell C8 is the value, and then in D8, we have the units meters per second. In cell B9, we put the label W number for wave numbers. In cell C9, we put 2134, which is the value for carbon monoxide. In cell D9, we put the label inverse centimeters. In cell B10, we put the label nu for frequency. We put the formula in cell C10 to calculate that. In cell D10, we have a label for the units inverse seconds. In cell B11, we have the label omega for the angular frequency. We calculate that in cell C11. And in cell D11, we have the units again of inverse seconds. And our final two defined variable quantities. In cell B12, we put the label alpha. In cell C12, we compute alpha. Alpha is unitless. In cell B13, we have the label capital N for the normalization constant. And in cell C13, we compute that normalization constant, which involves a fourth root. In cell F3, we put the label exponential, because this is the Gaussian part of the wave function. In cell F4, we have this particular formula where the $C $12 is the alpha value, G4 is the value of Y. Then we're going to copy cell F4 from F5 to F180. Then in cell G3, we put the label X. In cell G4, we have our minimal value for X here. In cell G5, we put a formula that is going to increment the coordinate to the right, and then we copy cell G5 from G6 to G180. Then in cell H3, we put the label psi sub 0, so that's the lowest energy eigenfunction. We have in cell H4, we have a formula, which is just multiplying the normalization times the exponential value. For this one, the Hermite polynomial is just 1, so it's implied. Then we copy cell H4 from H5 to H180. Then in cell I3, we put the label X. In cell I4, it's equal to G4, and then we copy cell I4 from I5 to I180. Let me note here again that the way we're setting up the worksheet is not the most efficient and uh, minimal memory way that we can do it. We're trying to do it in a way that's very clear and it's easy to see what's going on here. So we do a lot of repetition of this column of the x coordinates just to make it easy to see where it is. So in cell J3, we have the label psi sub 0 squared, that's the probability density. Then we have a formula in cell J4, and then we copy J4 from J5 to J180. Then again in cell L3, we have the label X again, and the formula is L4. We're just copying those values of X into different columns when we need to. We're not recalculating them. And then we copy cell L4 from L5 to L180. In cell M3, we have the label psi sub 1, so this is the next eigenfunction. In cell M4, we compute that. Note here that the Hermite polynomial is the square root of y. Then we copy cell M4 from M5 to M180. Again, as you'll notice, keep repeating this, but in cell N3, again, we have the label X, and cell N4 is the formula equals G4, and then we copy these values from N4 to N5 to N180. In cell O3, we have the label psi sub 1 squared, so that's the probability density for psi sub 1. In cell O4, we have a formula. Then we copy cell O5 from O6 to O180. In cell Q3, now we have the label 2y squared minus 1, so this is the more complicated Hermite polynomial that we're using. In cell Q4, we have a formula to compute that. Then we copy cell Q4 from Q5 to Q180. In cell R3, we have the label X again. In cell R4, again, we just copy G4. Those different X values just keep getting repeated to different columns to make it clear to see what the X value is. And then we copy cell R4 from R5 to R180. So it says 108 at the bottom of the slide. That's a typo. It should be R180. In cell S3, we have the label psi sub 2, so this is our third eigenfunction. In cell S4, we have the formula to compute it, using the fact that the Hermite polynomial here is that 2y squared minus 1, which is in its own particular column, computed separately for needing it. And then we copy cell S4 from S5 to S180. In cell T3 again, we have the label x. In cell T4, the formula equals G4. We just keep copying that over. And then we copy cell T4 from T5 to T180. In cell U3, we have the label psi sub 2 squared, so that's the probability density for the third eigenfunction. Cell U4, we have a formula to compute that, and then we copy cell U5 from U6 to U180. Then in cell W3, we have the label 2y cubed minus 3y, that's the Hermite polynomial there. In cell W4, we compute that from the value of y that's computed. You'll see in cell X4. We copy cell W4 from W5 to W180. In cell X3, we have the label y. In cell X4, we compute y, and then we copy cell X4 from X5 to X180. Let me mention here, as the Hermite polynomials get more complicated, just to make it easier to debug and keep track of things, we're breaking up the different parts of the Hermite polynomial and then combining it and then incorporating it into the eigenfunction. So in cell Y3, we have the label X4. We have the formula in cell Y4, so we copy it from Y4, Y4 from Y5 to Y180. In cell Z3, now we have psi sub 3. This is the fourth eigenfunction. In cell Z4, we have a formula to compute that. So then we copy cell Z4 from Z5 to Z180. In cell AA3, for the last time, we're going to have the label X. In cell AA4 equals G4. So we just keep copying that value of X across the worksheet. And then we copy cell A4 from AA5 to AA180. And the very last entry we make into our worksheet is we have cell AB3 with the label psi sub 3 squared, so that's the probability density there. In cell AB4, we have a formula to compute that, and then we copy cell AB5 from AB6 to AB180. So this gives us all the information we need for the first four eigenfunctions and their probability densities. So for the remainder of the video, we're just going to tell you how to generate the charts and then showing what the charts look like. Now, the generation of the charts is going to be very, very repetitious. So rather than me read it out each particular time, you'll be able to note or stop the video where this verbal description of how to fulfill each chart. So here is the eigenfunction psi sub Here is the probability density for psi sub 0. Here we have eigenfunction psi sub 1. Here we have the probability density for psi sub 1. Here displayed we have a chart of eigenfunction psi sub 2. Here we have the probability density for psi sub 2. Here is our last eigenfunction that we plotted in the worksheet. So this is psi sub 3. And here we have the probability density for eigenfunction psi sub 3. So we see as the quantum number n gets bigger and bigger, the probability density of the quantum harmonic oscillator begins to approach more closely the probability density that we would get for a classical harmonic oscillator. I thank you very much for your kind attention. Stay healthy, stay safe, have a good one.